Okay, so we're going to go through your paper 2. So a 4.406 sample of a compound containing only CHNO was burnt in excess oxygen. And it gives you the mass of carbon dioxide and water. Now, this is quite a common high-level question, but it's quite a difficult one. You're expected to apply what you know about atoms, moles, and empirical formula to this. So we have something with CHNO in it. And if it's burnt in excess oxygen, it's going to react with oxygen to make CO2 and H2O. And obviously we don't know those molar ratios. So we know the mass of CO2 is 8.8002. So 8.802. And water is 3.604. And it says we have the sample is 4.406. So we can work out how many moles of CO2 and H2O there are, and that ratio between those two molecules. So CO2 is divided by 44.01. Remember to use your 2 decimal place numbers from your periodic table. And water is 18.02. So we want to get our 2 moles there. So that gives us 0.200, 3 significant figures. The amount of you, if you don't put 3 significant figures, I'm going to keep marking you down because you will get marked down. Okay, so 0.2. Now, so that means for every mole of CO2, we have 1 mole of carbon. So that means that we have 0.200 moles of carbon. However, water, 1 mole of water, is 2 moles of H, or hydrogen. So we're going to have to times this one by 2. So we have 0.400 moles of hydrogen. So now we have our molar ratio of carbon and hydrogen, and we can work out our mass of just the carbon and just the hydrogen. So mole times ram of just those atoms is going to give me 2.402 grams and 0.404 grams. So now we know how much carbon has come out and how much hydrogen has come out. And that molecule that we started with has only got carbon, hydrogen, oxygen. So if we know the mass of carbon, hydrogen in it, we can then work out the mass of oxygen in it. So we're going to minus the mass of carbon and hydrogen. So that gives us 1.6 grams of just oxygen in that molecule. Obviously, we don't know how much O2 is there, but we're not worried about that right now. So now we can do our empirical formula. So we have our masses. We can divide our 3 masses by our MRs. So 16.00, 12.01, and 1.01. So that's going to give me 0.100. Run out of space on this one. Let's carry on over here. So I'm going to do oxygen, carbon, and hydrogen. So I had 1.60 grams over 16.00. And then I had 2.402 grams over 12.01, which is 0.2. And then I had for hydrogen 0.4 over 4 over 1.01 gives me 0.400. I mean, I didn't really need to work these ones out again because I had it here. Sorry, here. So I could have just copied it across. I didn't need to do it. I'm just doing it so it's easier for you to see. So now we have our empirical formula. So I can see that's a 1 to 2 to 4 ratio. So it's going to be C2H4O. So that is my empirical formula. Then the next one says, determine the molecular formula of this compound. So if we know that MR is 88.12, well, we want to know the MR of C2H4O. So it's going to be our 12.01 plus 1.01 times 4. It's going to be 44.06. So then I'm saying, how many times does that fit into my molecule? So I can see that's a 2 to 1. So that's going to fit in there twice, but I can do 88.12 divided by 44.06. So it's going to be twice as big. So it's going to be C4H8O2. So that's my molecular formula. Now, some people might have missed this sentence here. It kind of follows on to the next question. So we've got 3 spectrums that show propan-1-ol, propanal, and propanoic acid. Propan-oxalic acid. So it's going to be spectrum C is going to be our. So we've got our 3 spectrums here. So remember, we can ignore our fingerprint regions. And I always do this to make this easier, especially in exam stress situations. So I've got my CH bond there, but we don't need to worry about that. So that's my OH alcohol. And you can see this is more to the right, big broad OH peak. So that'll be an OH acid because it's more to the right. You can see it overlaps with that CH much better, but you can use your data books obviously as well. This is the COO. And then this is our CH peak again, and this is the COO. So you can see here spectrum A is going to be our alcohol. So that's 1-ol. So the spectrum B is going to be a carbonic acid. So propan-1-ol. And it's asking you to identify the compound, not the functional group, not the class, the compound. Acid. And now, reason, how did I know that? Well, I know this has a broad OH peak, and that you have to say the range as well. You can say the number it's on. I would say the data book range, just to be on the safe side. You'll always get the mark for that. So this peak will be at 3200 to 3600 centimeters minus 1. And then propanoic acid has a broad OH acid. You could put alcohol here if you wanted to. As long as you put the range, you're fine. Peak at 2500 to 3000 cm minus 1. Okay, and you have to say both. Has a strong COO peak at 1700 to 1750 cm minus. So I'm writing a bit big in this, apologies. And propanal has a strong COO peak at 1700 to 1750 centimeters to the minus 1. And you had to get each row correct to get the mark. So you get 1 mark for that row being correct, 1 mark for that row being correct, and you had to put both of those points for that one and 1 mark for that being correct. Explain the general trend in ionization energy. So remember, I told you there's 3 things we need to talk about with ionization energy. So it's got an increasing nuclear charge, or you could say number of protons. Okay, it has the same shielding or same number of shells. Remember, I said you need to say 3 things for this 1 mark. And actually, you didn't have to say that bit, but atomic radius decreases. Okay. White phosphorus is an allotrope. And phosphorus exists as P4. So I've got a P4 molecule. So, you can do dot and cross to work it out. P is in group 5. So it's going to, oops. and then it's going to have a lone pair. However, these ones don't have 3 bonds, so these ones need to have 3 bonds. So what they're actually going to have to do is each P needs 3 bonds to the other P's, and then they each have a lone pair, quite a complex molecule. Okay, they did also allow you going P, 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 and then each one needs 3 bonds, so you could do that with your lone pairs. Okay, so really unusual molecule. I'd be surprised if sort of barely any students got this question, in all honesty. But I wanted to put it in here just to show you what can come up and not to let it freak you out. You might get the mark, you might not, but it's 1 mark at the end of the day. Okay, don't stress about it. Don't let it take you too long. You can always skip it and come back to it if you have time. Remember, get your easy marks first. Collect all the marks you're able to get, rather than spending 10 minutes on a mark you may or may not get. So deduce the electron domain and molecular geometry. So your electron domain, you're talking about the number of atoms or lone pairs around an atom. So if I look at CH4, for example, CH4 has 4 atoms around it, no lone pairs. So that's going to have an electron domain of 4. And when we're talking about the shape, we're talking about what would that shape be without any lone pairs. So that would be tetrahedral. And then the molecular geometry is the shape of the molecule. So this time we're including lone pairs. So for this example, they would both be tetrahedral. Okay. But this one, they're asking us for PCl3. So I have PCl, Cl, Cl. P is in group 5. So 1, 2, 3 electrons there. So it must have a lone pair. So it has 1, 2, 3, 4 things around it. So that means its geometry, its electron domain geometry, is tetrahedral. And if you look at that sheet I printed out for you, the table with all the shapes and angles and everything on it, you'll see on the very left-hand side it says electron domains, and then it says molecular geometry, electron domain geometry, or basic geometry, I think it's worded as. So the actual geometry of the actual molecule, we have a lone pair, so that's affected our geometry. So it's actually trigonal pyramidal. Okay, and remember, tetrahedral is 1 in 9.5. If we minus 2.5 for every lone pair, that would give us 107. And it'll always give you within the range there by doing that. Okay, and the range they actually allowed was 91 to 108. Okay, so they give you quite a big range for that. Then it says explain the polarity of PCl3. So again, looking at this molecule, you've got your delta negative, delta negative, delta negative. Okay, and then you've got your lone pair up here, but your P would be delta positive because the chlorine is much more electronegative. So the difference between those would mean that the chlorine is pulling the electrons much more. Remembering that you have your Pauli scale, your electronegativity scale in your data books. So you can use that to help you if you want. So the polarity is polar. And it says explain. So you had to have the explanation as well. So you could either talk about the fact it's not symmetrical. You could talk about the fact because this side of it is negative, this side is positive. The dipoles don't cancel out, whereas on a tetrahedral molecule or a symmetrical molecule, it would cancel out. So you could say the dipoles don't cancel, or you could have said unsymmetrical, like distribution or spread of charge. Or you could literally describe the picture so that you have a delta negative side and delta positive side of the molecule. I'd be tempted to include the diagram if I'm using that explanation. Okay. Question 4a. 1-chloropentane reacts with aqueous sodium hydroxide. So we've got hydrogen alkane and a hydroxide. So the type of reaction is going to be nucleophilic substitution. Be really careful on the wording here, because they're asking for the type of reaction, not the mechanism, which, strictly speaking, that's not the type of reaction, that is the mechanism. So just be really aware that they're using that wording when they are asking for mechanisms. 4b, outline the role of the hydroxide ion in this reaction. Well, it's acting as a nucleophile because it's nucleophilic substitution. So it acts as a nucleophile. You could describe that, so you could say it donates a pair of electrons. Okay, or you could say it acts as a Lewis base. Where we do acids and bases, that'll make a bit more sense, but basically a Lewis base is an electron pair donor. We kind of wrote it in our notes, but haven't really talked about it. We'll talk about it a lot more in acids. Suggest with the reason why one iodopentane reacts faster than one chloropentane under the same conditions. So what's different about these molecules? Well, one has that Ci bond and one has a CCl bond. Apart from that, they are the same molecule. So in other words, what's different about those two bonds? It says use section 11. So that means you need to use section 11. What is section 11? Well, section 11 is bond enthalpy. So you can see the values for the bond enthalpy of these two things. So you can actually state the bond enthalpies. You can say the bond enthalpy is lower for Ci and CCl. Make sure you don't just say it's lower or bond enthalpy is lower, okay, because they won't know which one you're talking about. You need to make sure you're specific and the examiner knows what you're talking about. Okay, or you could say it's weaker, but I would try and stick to the bond enthalpy is lower rather than it is weaker. So this means it breaks more easily, or better would be with less energy. Okay, or you could give the values for this first mark. Okay. 5a, outline why metals like iron can conduct electricity. So metals can conduct electricity because they have delocalized electrons. Or you could say delocalized sea of electrons. Or you could say mobile, if you're not comfortable with the word delocalized, which is fine. Justify why sulfur is classified as a non-metal by giving two of its chemical properties. So it'd be really important. Some people gave me physical properties and things like that. So non-metals. So what's different about a metal and a non-metal? Well, non-metals form acidic oxides. Form acidic oxides. Non-metals, they covalently bond with each other. So they form covalent compounds with other non-metals. They form anions rather than cations, or negative ions. Try and stick to the word anions if you can. If you're worried you're going to get confused between anions and cations, then that's fine, use negative ions. And they behave, so because they form negative ions, they take electrons away from other things. So they behave as an oxidizing agent. So those that you did IGCSE last year should be able to get that one. Some of you may not have done oxidation reduction before. And they actually allowed 1 mark if you had 2 correct non-chemical properties, but I don't think anyone got that mark particularly. So describe the bonding of this type of solid. So iron sulfide, so metal and non-metal, so it's ionic. So what is an ionic bond now? The metal gives an electron to the non-metal. That is not the bond. That is how the ions are formed. The actual bond itself is once that process has happened, we have those 2 ions. So it is an electrostatic attraction. Okay, between oppositely charged ions. or you could say between a negative ion and a positive ion, or you could say between Fe2 plus and S2 minus, but being aware that if you got those charges wrong, you would lose the mark. So I would just stick to saying oppositely charged ions or positive and negative ions. 5D, outline in terms of electronic structure why the ionic radius of sulfide is greater than oxide. So a sulfide ion, so sulfide forms 2 minus. So normally sulfide has 16 electrons, so that's going to have 18 electrons. Oxide forms a 2 minus ion as well, so that would normally have 8 electrons, so that has 10 electrons. Okay, so we don't need to go into too much detail. You can see that sulfur has an extra shell. So you could say it has an extra electron shell, it's in the third shell, you can give me the electron configuration, things like that. So I would just say there's an extra electron shell. Okay, you could have done 2, 8, 8, 2, 8. Kind of old GCSE style, just talking about the shells rather than the subshells. You could do subshells as well. 5E, suggest why chemists find it convenient to classify bonding into ionic, covalent, and metallic. Now, I put this in because IB do this random thing of putting these kind of strange questions like this in where they want you to kind of talk about around the subject a little bit, or sort of looking into, I guess, the TOK kind of area and things like that. So it's kind of like, why do we use these models? Why do we generalize things? Why do we have standard names for things? Anything like that. But they're usually pretty liberal on the mark scheme on what they allow. So there are some suggestions on the mark scheme, but it also says accept other valid answers. So for example, it says allows them to, I'll just give you one reason for now, but allows you to explain the properties of different compounds. They also said you can enables them to generalize about substances or enables them to make predictions. So anything along those lines, or anything that's just logical or sensible about why they would do that. So why do we group anything? But yeah, it's just a good one to have in there because I quite like doing those strange questions. So we got chlorination of methane. Show the initiation and propagation steps. So initiation is always the free radicals being formed. So it's chlorination, so we're going to have chlorine molecule breaking into 2 free radicals, and remember it needs UV light. We then have one of those free radicals attacking the alkane, so in this case it's methane, so CH4. And remember, it always steals a hydrogen to begin with, and we're left with our free radical, alkane free radical. So then we have our CH3 free radical, and I'm going to add it to my whole chlorine because I can't add it to a chloride free radical. That would be a termination step. So then it forms CH3, Cl, and a chlorine free radical. Okay, so they're your free radical steps. They do allow you to not just do structural formula, but I would try and stick to structural formula because most organic questions you need to, and it just helps you see the pattern and things. I don't know why they put this extra random box here. I guess it's in case you need space. Bromine was added to hexane, hexonine, and benzene. Identify the compounds that would react. So obviously hexane. Now hexane will react with chlorine, but only if it's bromine, only if it's a free radical. So there's a well-lit laboratory. So I'm going to assume there's UV light. So hexane will, hexonine, anything with a double bond will, because that's electrophilic addition. Benzene won't, because it will only do substitution. So it'd be hexane, and if you were worried, you could put with UV light, if you were worried about making that generalization. Or you could put with enough UV light or something like that. Okay. Here we've got PVC. State the structural formula of the monomer. It doesn't say whether it needs to be condensed or not, so I can draw it out or not. Now remember, every addition polymer like this has to have at least 2 carbons because it's the double bond we're breaking. And I can see the pattern is repeating there. So that is my repeating unit. So my repeating unit, my monomer is just my repeating unit with a double bond put in there instead. So it's going to be C double bond C, H, 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 Cl. They also allowed you to do condensed structures, so CHCl, CH2. Okay, or you didn't need to put that, so CHCl, CH2 would have been acceptable as well. If you put the molecular formula, they wouldn't allow that. Okay, because it doesn't show that you understand that double bond is being reformed. The Bombardier Beetle sprays a mixture. They love these questions with weird molecules. We don't really care what these molecules are. So there's our reaction. Identified the species responsible for the peak at 110. So I'm going to work out my MR of both these compounds. So my hydroquinone is going to be 12 times 6 plus 4 plus 32 plus 2. So that's 110. I'm not worrying about the decimal places just for now because they haven't included it here. And then this one's going to be 6 times 12 plus 4 plus 32. So that's going to be 108. So the thing that's going to be responsible is going to be this hydroquinone. Now, what you need to be careful of is in order for it to be detected in a mass spec, remember it has to be a positive ion. If it's not charged, the detector won't be able to detect it, produce current, etc. Okay, so it's going to be C6H4 OH2 plus. If you do not put that charge, you cannot get it. Okay. Would be it's MR. So the idea is you should know that it's the MR that is going to be. 7B. Identify the highest MZ value of quinine. So the highest one we could possibly wait. They wouldn't allow you anything where you're trying to read off the graph. So it has to be exactly 1.8 or 1.8 with your decimal places if you calculated it fully. So phosphine is a hydride of phosphorus with the formula pH 3. So we've got 2.78 phosphorus. Calculate the amount of moles of white phosphorus. Okay, most of you are pretty good at identifying which question you were talking about. So it's going to be mass over MR. It's going to be 2.478 divided by your MR. So P is 30.97 and there's 4 of them. So that's 0.22. And again, 3 significant figures. Moles, always 3 significant figures. That hasn't changed from GCSE. Might have used one significant figure. This phosphorus was reacted with 100 centimeters cubed of 5 mole sodium hydroxide, deduce which was the limiting reagent. So let's work out our sodium hydroxide moles. So it's going to be concentration times volume. So it's going to be 5 times, and remember, volume is going to be 100 divided by 1,000 because we need it in decimeters cubed. So that's going to be 0.5. Now our P4 to NaOH or OH minus ions is going to be 1 to 3. So 0.5 divided by 3. That's going to be 0.16 reoccurring. And you can see 0.02 moles of P4 is less than 0.16 reoccurring, so therefore it's limiting. Okay, so make sure you're clear. So you needed the moles calculation and the fact that it's limiting for that. Question 3. Determine the excess moles. So our excess reagent was sodium hydroxide. So we had 0.5 moles of sodium hydroxide. So minus how much we would have made. So P4 to NaOH is times 3. It's going to be 3 times our moles of P4, which is 0.02. Which is going to give us 0.4 544, 0 moles. And question 4, determine the volume of phosphine in centimetres cubed. So our moles of phosphine, it tells us phosphine is pH 3 at the top here. So pH 3 to P4 is a 1-to-1 ratio. So we're going to have 0.02, because that's our moles of P4 there, moles. How do we work out the moles of a gas? We're going to times it by 22.7. Okay. And then we're going to divide that by, times that by 1,000 to convert it into centimetres cubed. So that would be 454 centimetres cubed. You can use PV and RT, but you're going to make it a lot more complicated for yourselves. But it had to be in centimetres cubed for you to get that mark. And each answer, you had to have both of these for this answer. Each answer is 1 mark. State the name, applying the IUPAC rules. So here it's a lot easier if you draw it out. If you're not sure, so I've got 3 C's in a row, and then I've got a double bond C here. I've got my hydrogens, got 4. So that's my molecule. So what's my longest chain? Well, it's going to have to include my double bond. So there's my longest chain, or if you're looking at this molecule, doesn't matter whether you go to the up one or the down one. So that's going to be propene. Doesn't matter where I put the double bond, so I'm just going to, so it just needs to be propene. And it's got a methyl group. If it was at the end, it wouldn't be a methyl, so I don't need any numbers for that. So it's going to be methyl propene. Okay, so you shouldn't have any numbers for that one. The next one, draw a section showing 3 repeating units of one polymer. So remember, we're always looking where the double bond is. So this is my double bond. What 4 things are they bonded to? So on this carbon, I have a CH3 and a CH3. On this carbon, I have an H and an H. So that double bond's going to get broken open, and we're going to end up with that. So that's my repeating unit. But I need to draw 3 repeating units. So we're going to have 1, 2, 3, 4, 5, 6. And it's going to alternate. So we're going to have, that one has 2 H's, that one has 2 CH3s. And then you need to extend your bonds out with your square brackets. Okay, you actually didn't get marked down if you didn't put the N for that one. So then compound A is flammable, formulate an equation for its complete combustion. So you come and put structural or molecular formula for combustion, it's fine. And then, so that's going to be plus O2 makes CO2 and H2O. So the first thing I always balance is my carbons first, so that's a 4. And then balance my hydrogens next, so 4 times 2 is 8. And then I'm left with my oxygen. So on the right I have 8, so 6 O2. Okay, so we have compound A there. So then next question, state the term that is used to describe molecules that are related to each other in the same way as compound A and compound B. So I'm just going to draw it here to make it easier for myself. Okay, so how are they related? They both got 4 carbons, and then they both have 8 hydrogen. 3, 6, yep. So they have the same molecular formula, but they have different structures, in this case different functional groups. So this is a structural isomer, or you could be more specific and say a functional group isomer. So structural or functional group isomer. So suggest a chemical test between A and B. So B has that double bond in it. So the test is going to be bromine water. And with A, it's going to go orange to colourless. The observation with B is it remains orange, or it stays the same colour. Don't just put orange. You could put yellow or brown. They allowed yellow or brown for that as well, or for both of those. Spectroscopic methods could also be used to distinguish between them. Predict one difference between the infrared spectra and the HNMR spectra. So we're looking at the difference between the methylpropene and the cyclobutane. So in the infrared spectra, you'd have a C-C double bond at 1620 to 1680. Okay, or you could say it would absorb at that. And because they say the difference, you would say and B would not. So make sure you state that it is different. The HNMR spectrum, so there's a few signals. The easiest one to do is that A would have 2 signals, or they're allowed peaks for that, and B would have 1. But they did allow that A would have a signal at 4.5 to 6 and B wouldn't, or A would have a signal at 0.9 to 1 and B wouldn't, or that B would have a signal at 1.3 to 1.4 and A would not. Okay, so there's a few things you could have said there. I think the easiest one is just the number of signals. You don't need to work anything else out then. That's a bit more space to write that correct answer. A sample of compound A was prepared in which 12C in the CH2 group was replaced by 13C. State the main difference between the mass spec of this sample and that of the normal compound. So obviously it's going to have a higher molecular ion peak. No, you could written this in the box as well, sorry. A higher molecular ion peak at 57. You could say rather than 56 if you want to be more precise. And then the number of protons would be 6 and 7. The atomic number 6. And this is 13 minus 6. So the mass minus the atomic number. What's the orbital diagram? If it has 6 protons, it must have 6 electrons. So 1, 2, 3, 4, 5, 6. State the symbol notation. So A is your atomic mass, and Z is your atomic number. So it would be Mg2612. Last one. Mass spectroscopic analysis, of a sample of magnesium gave the following results. Calculate the relative atomic mass. So it's your abundance multiplied by your mass, all added up, divided by your total abundance. It's your weighted mean. So it's going to be 78.6 times by 24 for this first one, plus 10.11 times 25 for this one, and plus 11.29 times 26 over your total abundance. And be careful because it's not always 100 when it's percentages, because sometimes it's comparable percentage. In this case it is. So that's going to give you 24.3269. So you need to write RAM to 2 decimal places, just like your periodic table. So it'd be 24.33. Okay.